Hello everyone. So welcome to the next lecture on this course. Where we ended up last time was that we were discussing about climate models, and we thought that we will go deeper into this to understand that how does the future scenario looks like. We have already discussed that how things are changing in terms of climate, and also we had also discussed that it is carbon dioxide which is primarily responsible. And we also saw that the emission of carbon dioxide and other greenhouse gases has not gone to zero yet, and actually it is still not started on reducing trend also yet. Though the growth of them has reduced, but still they are still on the upward trend. Now, what scientists are trying to predict based on whatever is happening currently, and if we continue the way we are functioning as of now, they have been using a lot of modeling tools to understand that how the future might look like if we continue the way it is. And also then on top of it, what they have been trying to predict, or what has been developed as models, is that what happens if some intervention starts coming, and what happens if some intervention starts coming in some systematic manner in some specific sectors, what all scenarios can be built up around it. For that, there is a complicated science, as I was discussing in the last class with you, that this whole is done through a science called climate modeling. And in climate modeling, what has been done and what is being done is that over the years, the demand from climate model has evolved. So initially, which used to be just atmospheric model, which used to just predict the weather and that how weather will change over next day or so, or like it used to be just a tool for weather prediction. It has kind of evolved into a multi-dimensional tool over the last few decades. So, like in 1990s, what it got involved with this, the land surface interaction issues, much more science kind of evolved around that. Then ocean and sea ice issues were integrated in the 90s in this model, because there were very clear indication that that needs to be understood better, because what scientists noticed was that there is a definitive change in ocean and sea ice phenomena, and that needs to be incorporated rightly and understood rightly for them to predict the future trends better. Then, as we already discussed, that ozone issue came in and surface aerosol issues become very popular. So, in 1990s, what started getting included in these models was surface aerosols. Specifically, it started with ozone journey at that time, and then non-sulfate aerosols also came into picture. Like, so, initially it was the sulfate-based aerosols which was prime focus of interest because of obvious things that we discussed. Then non-sulfate aerosols also started coming into picture. And then also what is happening right now is that even carbon cycle is being put into this whole thing, because as I discussed, that there is a slow carbon cycle, there is a fast carbon cycle, and how is that reacting, how is that expected to react as things are evolving. Because as remember, the current carbon cycle, whatever way it is functioning as of now, is going to happen is a very strong word, and as a modeling person we should not be talking about that term at all. But what might expect is that as the dynamics of this whole system is changing, as ice is melting, as sea is getting acidic, as the amount of GHGs in the environment is changing, all of this can lead to a different situation with respect to carbon cycle absorption behavior also. So, it is not only the specific after weather issues, but the carbon cycle itself can get impacted, as I discussed earlier. So, that is now also being modeled. What is expected to come in these coming models, as I was ending last time in my lecture, was that more dynamic vegetation issues, atmospheric chemistry, try to understand this at a much deeper level, because if we really want to understand the climatic changes going forward, we want these studies to also be part of these climate models. And even with advent of AI and ML, I think these models will evolve much more faster pace in coming decades is what is expected, and that is the need of the hour, because we want to have a better prediction of things as they kind of come along. So, just to understand, we will not go into real science of these models as such, because that is much beyond the scope of this course, but we will at a very high level try to understand that what these models do, how do they function, and just kind of giving you kind of a framework in terms of these models. And again, to repeat myself, I will not go very deep into this, because that is not my area of expertise, but beyond that it is much beyond the scope of this course. So, these models are usually developed at two levels or actually multiple levels. One is a global climate model where we try to understand it at a very macro level in terms of about 100-kilometer resolutions, where we try to understand at a very big grid level what is happening. And in this case, what we are trying to look into that at a broader level, what is expected in terms for climate to happen. We are not very concerned about the local area effect in this case. There are some averaging at a local areas which can be done, but what we are trying to understand really at a global scale, what is expected to happen. The subset of that, or maybe a second category of studies in this line, would be regional climatic model, where the resolutions is much higher compared to global climate model. At regional level, the resolutions can be in tens of kilometers, it could be 20-30 kilometers or even 10 kilometers at times. They are nested within GSM, like global climatic GCM, within the global climatic model. So they use the boundary conditions of global climatic model, but overall they try to look at the impact at a much higher resolution, because we want to understand at a specific geography level, at a specific area level in terms of expected changes, and we try to kind of integrate at times these regional climatic model into global climatic model to understand, have a more fine resolution picture at a higher level also. But overall, the temperature, wind conditions, they are kind of kept same in both the models, because of course they will remain same, but resolution of those wind currents, resolution of those temperatures are done at much finer level in regional climatic model. Purpose is that you want to understand the regional impact, as I mentioned, right. How the various models are integrated. So basically in terms of the 4 subsystems are usually done. You take care of the atmospheric conditions, we handle the land surface issue, as I mentioned in the various model phenomena. We look at the ocean and the sea ice issues specifically, and these are the 4 broader categories of elements that we are trying to understand, and we understand all these issues in terms of their physical characteristics, in terms of their chemical characteristics, and in terms of their biological processes also, because all of them are not independent, but they are intradependent or interdependent also. So we need to really understand the interface and interaction of these models also. Usually these models are done with a clear circulation picture in mind, which looks into resolving flow of heat, flow of moisture, momentum of these things, how momentum is changing, how momentum is expected to change, and it kind of leads to a like global energy balance equation. What is expected is that it will lead to a kind of a long-term climate prediction is at a global level is what is expected to kind of come. And basically why these 4 elements is kind of considered is because at atmospheric level, what we are trying to look into is that we are looking into cloud dynamics, we are looking into aerosols, we are looking into radiations at atmospheric level, we are trying to look at global heat water transport, very broad parameters of atmosphere at that level. For land surface, we are trying to look into vegetation, how the vegetation is changing, how vegetation is currently, how it is expected to change, soil moisture, hydrology. At ocean, we are, I am just naming a few points here. At ocean level, we are trying to look into carbon uptake, we are looking into biochemistry of the whole thing, we are looking at the thermodynamics of ocean, how it is changing. At sea ice level, remember we talked about albedo effect, so we start looking into albedo effect, we start looking into freshwater exchanges, because that changes the temperature and the chemistry of the sea on a continuous basis. For a regional level, the things are pretty similar, the parameters remain same, but what happens is that the resolutions is much finer, and there we are able to look at more complex topographies, we are looking into coastlines, we are able to look at sea water contrast at a very fine scale, and we are even go as high as a kind of a coastal line, and we can try to see the interactions and things evolving at that exchange also. What is the strength of such a model is that it kind of gives regional extremes, it gives a terrain and atmosphere interaction much more finely, because that sometimes can lead to a much more complicated global modeling or global issues, which will get ignored if we are trying to look into this at a broader level, right. Sometimes what happens is that this is much more computationally extensive, as you can understand that since the grid lines will be much finer, so computationally it is much more extensive and exhaustive also at times. and at the same time it carries on some biases from the global climatic model, because once we are assuming some kind of boundary conditions at a global climatic model, at that level sometimes those biases might continue and come into regional climatic model. So we need to do sometimes these statistical correction, and we need to come up with the more correct picture if we really want to look at the regional climatic model at that level. Basically, there are further scenarios around it. So the scenarios are, then we talk in terms of RCPs, which are representative concentration pathways, which provide a very high level of understanding at a physical risk analysis, such as rising temperature, extreme weather conditions. We look at those issues. We look at socio-economic pathways, where we look into socio-economic dimensions. We try understanding that how the social trends might change, how it might impact the policies that specific geographies needs to work upon, or at globally how we need to look at policies. And basically integrating this together can come as a more identified resilience strategies can come in, because on one hand you are trying to look at the standard pathways in terms of how things are evolving at a worldwide level, and on the other hand you are trying to also look into that how those evolving things are impacting the societal thing also. So if you kind of integrate these two things, we can come up with a much more comprehensive policy framework. We can also come up with better regulatory framework, and also we are able to predict with some of these models, with of course some uncertainty built into it, is that how things might evolve up to 2100, while, and also not only looking at 2100, but we can also look at year on year kind of a scenario, or maybe a decade by decade scenario, that if things continue the way they are kind of carrying on, what can happen in next few decades or something like that. For example, RCP 8.5, which is under IPCC framework, it projects that the global mean temperature may go up to 4.8 degrees centigrade, as high as from current baseline of pre-industrial era, or the global temperature can go as high as up to 4.8 degrees centigrade. While RCP 2.6, which is slightly different model, says that we can limit it to about 2 degrees centigrade. So it really depends upon the which scenario you are looking into, that there could be multiple scenarios, there could be multiple assumptions which kind of go into this, and I'll talk more and more about this. But what you need to understand and take it as a key thing right away is that any of these models are not sacrosanct, or any of these models are not a perfect recipe for future predictions. They always work within a band, they always work within some uncertainty, and they will give you a prediction which will have some kind of a probability attached to it, that probability of event happening might be very high, or there could be a low probability of that event happening. And you need to really understand that what is the variance of the predicted value around the mean value, that you need to really watch out for that very carefully before you kind of make any broad claims around it. The models can be on multiple kind of various models can be brought in. We can have energy balance model, where you can be just looking into energy, how the energy is getting balanced. We could be looking at radiative convective climatic models also, where we are trying to look into that how these atmospheric composition and investigation are likely to influence the different external and internal forcing, how radiative forcing is going to change the dynamics of the whole atmospheric condition, how radiative forcing themselves are expected to change with some of the inputs that we kind of talk about. We also have circulation models. So there are multiple ways in which you can just look into these models. How you usually do it, these models, is that you kind of have a fixed variables which goes as input in these variables, and sometimes there are fixed variables, sometimes there are time evolving variables. Like fixed variables could be parameters related to earth, parameters related to solar constant, parameters related to atmospheric compositions, which is much more fixed in nature, which is a long term change, and even if it's changing or evolving, those are very slow moving changes, and they kind of evolve over period of time. While there could be some time evolving variables also, which could influence the model in next few years, but and these parameters are changing with time, like wind conditions, sea ice thickness, ocean heat content. They are evolving, they are changing. Biochemical traces, those are changing and evolving. So they keep on evolving, they keep on changing, so they need to be handled at a different level. Then from these two things, we kind of come up with some kind of a derived variables also, like which are not directly input as a variable, but they can be derived variables, but they have an impact on our final output of the whole situation, where some of things like surface albedo effect. So that could be a derived parameter rather than a direct parameter, which can be probably modeled in. We can talk about energy components like kinetic energy, potential energy, or latent heat energy of the system, this aerodynamic system, which could be an evolved thing depending upon the mass and the speed of the wind and many other parameters. Some of these parameters could be derived, and so they will have their own impact, but these are all put in. Then what we finally do is that once we have taken all these parameters, then we kind of put them into a grid or understand them at a broader level, but then we divide the whole thing into the grid units. As I said, that at a global level we divide that grid into hundreds of kilometers of grid. At a local level we divide that grid into tens of kilometers or 5 kilometers or anything of that sort. And once we kind of divide that into grid, we understand the issue at a specific grid point level, and then we integrate the whole thing, and then we kind of understand the broader picture. Once we have done all that, and once we have put that through a modeling process, we put some criteria for selecting climatic scenarios, and the criteria could be like we need to have a consistency with the global projection, because we cannot suddenly be talking something which is out of air, that it is something which is very different from what we are talking today, because sometimes modeling can give you some parameters which are not physically possible or something which are not plausible also. So just to avoid those situations, we always look into that, are we consistent or are there outliers which are happening. I'm not saying that we need to be biased and only talking about whatever we are predicting today and we are just trying to put a linear line to that, but at least it should be physically and conceptually consistent with whatever we are discussing as of now. We should be able to look into physical plausibility of the event happening. It should not be something that is something which is not possible at all, and we kind of predict that as a model. Like for example, all the glacier ice melting in next 2 years. Like some extreme equations can simply say that, but we also all know that that is not physically possible. So we have to ignore those specific events happening, or so that is something which we kind of need to ignore. We need to also see that whatever we are predicting should have an impact applicability in impact assessment. It should not be some parameters that we are just doing from academic sense perspective. At times there could be some parameters which could be academic in nature, but they also should have derived inferences on the impact assessment that we need to kind of keep in mind, because remember, why we are doing all this modeling is that we are trying to find out that whatever is happening at a global level, whatever is changing at a global level in terms of climate, we want to have a understanding that how it is going to impact the future climate or future evolution of the climate thing. And it should be accessible, like we should be able to obtain these results at a click of a button, or in terms of accessibility, it should not be something which is hidden somewhere, or it's very difficult to derive, very difficult to infer, very difficult to understand that what is happening around at the final output level. So that those results should be very accessible in nature. Before we move forward, there is a word of caution, as I mentioned earlier also, but just for sake of repeating and understanding that why it happens, is that there is a lot of uncertainty in these climate models. Why these uncertainty is there is because we are talking about a complex system of physics, chemistry and biology here. So physical system, chemical system, biological system, all are evolving. As I said, that there are some fixed variables, there are some dynamic variables, there are some time dependent variables which are there. Since the variables are evolving and there is always a predictability around how these things will change, then nobody can for sure say that how much it will snow next year. There will always be a band in which we are talking about, right? So there is always a variability within the parameter itself, and given that variability within the parameter itself, the model will always give a value which will be within a tolerance limit only, and the variability around that, there will be variability around incomplete knowledge. Like we do not understand the whole interdynamics of the systems at 100% level, but now though the science has evolved a lot, but you need to understand that these models have to be taken with some word of caution, that these models will not give you 100% accurate results. there are more uncertainty also, like so while there are model based uncertainty, while there are nature variability which is there, there is another thing which is there is a scenario uncertainty, because which scenario things will evolve in. Like so socially, for example, how things will evolve socially is always a prediction around the whole thing. How the societies will evolve, how much of population will move from rural area to urban area, how much of industrialization will happen in which cities, how much of construction of cities will happen, how much of sand will be used, how much of cement will be used, how much of iron will be used. There are multiple dynamics of the whole situation, because that will depend upon the economical growth of an area, some intercontinental issues, some political dimensions also evolving. Like nobody could have been very rightly predicted that there will be 3-4 wars going on in the world as of now. Maybe 10 years before, nobody could have predicted that. So like for example, what happened with the Russia-Ukraine war is that Germany had to restart many of its coal plants. So that was something which was not predicted in the model. So those kind of uncertainty scenarios will always be there in the background, and we need to kind of understand that these uncertainty scenarios will always lead to a situation where we can have these models giving results which are very different from what we are observing today, or it could be slightly different from what we are observing today. And so they always needs to be taken with a word of caution, and we need to have a broader understanding of the subject before we commit onto any of these numbers. Some more uncertainty which can come in these models is because of how the technologies will evolve in future, how the policy decisions will change. I already talked about social behavior and economic growth things. So there are multiple emission scenarios which are evolved based on all these uncertainties, and then all of these models are having some kind of a window in which they need to be looked into, and there are a lot of assumptions which are going in there, and there are a lot of kind of a understanding that needs to be developed before we can start using these models in totality. But overall, what you need to understand is that there is a whole science behind all these predictions, but with all the evolved science, with all the evolved modeling power that we have today, there is a high level of uncertainty in all these models. And so these models needs to be taken on a face value up to an extent, and beyond that there has to be some kind of a understanding which needs to be developed for these models for us to claim on many of these numbers. But having said that, these models are highly useful for us, because with them we are able to make some sense of things which may evolve in future. Without that, for us to react in future once things have happened would be very difficult, and we might be at a situation where things might not be in control at all. So while many scientists say that we are crossing the tipping point day by day much faster than we should, but if we did not have these climatic models with us, maybe things would have definitely crossed some of these control points, or tipping points would have been crossed if we did not have these climatic models available with us, right. I can continue with this uncertainty, but you can understand that there is a model level uncertainty which I already talked about, I guess. There could be some natural variabilities also, like some volcanoes will erupt, some changes in solar radiation might happen. There could be some ocean atmospheric interaction like El Nino, La Nina, those kind of short term phenomena can also be there, which can lead to some different scenarios, and which can actually lead to a different weather condition and leading to a different climatic condition on a short term basis to maybe even at times year on year or decade level variations also. So overall, there is a high level of unpredictability on all these models, and but still they give a direction. Now having said that, let us try to understand these numbers in some better terms now. So the first graph that I am going to talk about is future CO2 concentration predictions. So as we understand, the current CO2 is about 420 ppm in air in our atmosphere. So so there are multiple scenarios which has been developed around this CO2 predictions also. So the average line which kind of falls around is that if you look at this black color line, this is kind of an average line. So look at the black line which is happening here, this line. If the things continue the way they are, like if business as usual kind of continues, our atmospheric ppm of CO2 might go as high as almost 750 to 800 ppm at the end of the century, which will be almost double of what we have today, right. So But on the other hand, there are some variability around it, with some variability around it, the carbon dioxide may remain at about 600 ppm or 700 ppm, or it can go as high as about 900 to 1000 ppm also at the end of the century, right. This is about what we need to understand is that if we continue the way we are continuing right now, we might end up at a much higher CO2 level predictions, and all these models, now it will depend upon the CO2 concentration, that what will be the end temperature for us in the atmosphere, right. So if CO2 is predicted to increase the way it is predicted, we could be looking at scenarios which could be much higher temperatures, but none of the scenarios is still talking about that we could have a situation where a ppm level of CO2 will start going down. That is a very clear indicator, and that is a kind of a scary proposition. So it means that in all likelihood scenarios, our temperature will continue to rise. How much it will rise depend upon the final CO2 concentration that we have at the end of the century, or there could be some temperature level behavior also, which again I will show you. In terms of climate projections, this shows that how the average temperature might rise, and these use CO2 emissions directly and also include the carbon cycle feedback, because remember we have a carbon cycle feedback which is also evolving with changing dynamics of our atmospheric condition, because the sea is changing its behavior, vegetation is changing its behavior, and with all of them changing its behavior, what we are seeing is that they also have an impact on how much carbon is CO2 is absorbed by this whole system. But after correcting for all the other greenhouse gases, it is expected that our temperature may increase from anywhere between 2.5 to 6 degrees centigrade from the pre-industrial era by 2100, which is much beyond what we are even experiencing today. What it would mean is that it could lead to a situation which could be many more cases of droughts, many more cases of uncontrolled rains or rains in buckets, cloud bursting, and all those things, whatever we are observing over last 5 to 10 years, they may intensify much beyond if we kind of continue to go the way we are going. The typical projections that we are talking about is 2 to 5 degree centigrade scenario under IPCC AR4 scenario, and what is happening is that CO2 concentrations are likely to go up very roughly to 820 to 1100 ppm. In a high emission world, temperature prediction is going to go up by 2 to 6 degrees centigrade. So this very clearly shows that we are going to go much beyond the warmer path right now. But of course, as you can see that there is a lot of variance around this central value. This central value is not fixed, and which I have been kind of saying from earlier discussion also, that there will always be some amount of variability, which is a high amount of variability. Sigma values are very high around a central value, which is always the case in all of these projections. But what does these do? Multimodal warming projections tell us is that in high emission scenario, our temperature is expected to go up by about 3.5 to 4.5 degrees centigrade. It's a all likelihood if we continue the way we are continuing, if we don't do any interventions in a very short period of time. So there are models which can go plus minus 1 degree centigrade around it. So it represents a world with very rapid population growth and with a high fossil fuel emission, which is the situation as of today. So if we continue the same path, we may be warming as high as that. If we start controlling and we go with a more balanced energy mix, where we start working on fossil and renewables though has started showing good traction of late, and I will show you those numbers in some of the coming lectures, but still they have a very far reaching numbers to go for. In that case, still the temperatures will rise up to 2.5 to 3.5 degrees centigrade, and models kind of vary around plus minus 0.8 degree around the some central value. In a very strong shift over cleaner technology and sustainability, which is not happening as of today, we will talk about it more. But if we are able to do that, then potentially we will be able to limit our global temperature rise up to 1.5 to 2.5 degrees centigrade, which looks to be the best case scenarios of today, which is still scary, but that seems to be the best case scenarios of now. So three cases: first case is about a very high emission, second case would be kind of a medium kind of an emission which is happening, and third one will be kind of a low emission kind of a scenario which will happen. How the rainfall extreme might change by 2500. So it says that in low emission case we could have about 3 to 5% strong rainfall on wet days, which is higher than what could be potentially controlled, but it's still controllable. In case of medium emission, it can rise up to 6 to 8% increase on very high rainfall days. And in very high emission scenarios, since there could be some very high accumulation of moisture on a shorter geographical locations, it could lead to more issues of cloud burst. It could lead to issues where more intense rain in a very short duration can come in. So it could lead to a situation of 8 to 10% increase in the rainfall in a very short scenarios. So as some parts of Africa are expected to even go to a 10 to 20% stronger rainfalls, which would mean catastrophic issues for those specific geographies, because there could be issues of high cloud burst, there could be issues of flooding, there could be issues of even some of the areas getting permanently submerged, or some localities getting very highly affected. So we will continue this discussion in the next class, but just to understand that there is a strong science on climate model which governs how the climate is expected to evolve going forward, and it also governs in terms of that it then throws out some numbers at us which can be used as a predictive numbers going forward. And based on these numbers, we are able to make some sense out of the whole situation, where we are able to tell that how we can predict our weather to kind of move forward as we kind of go along. And but we need to take these numbers with some caution, as there is a high amount of unpredictability around these numbers, because these are all predictive numbers, not numbers with very third decimal place of accuracy prediction, which can be done mathematically. That is not mathematically possible. We will look into some of these scenarios more in the next class, where we will understand that what are the other weather parameters are going to change, and then we will look into that, are we reaching a point where our climate might already be reaching some of as we call it a tipping point, that we might already be crossing some of these tipping points, or what are those typical tipping points where we need to we might be reaching a situation where we might have a point of no return on some of the cases. Thank you, and see you in the next class.